In this video, we're going to see a more general version of Grover's algorithm. So here the setup is we have a Boolean function f that takes as input an n-bit string and outputs 0 or 1. And we're still going to have the restriction that we're promised that there's a unique x with f of x equals 1. Okay, and our goal is to find this x. And I'm going to call this x the marked element. Okay, so you see that this setup is kind of similar to what we saw in the first simple example where we just had, where n was 2. We just looked at a 2-bit function. Okay, so there are basically, 2 to the n possible f's that we are seeing as our input. Okay, depending on which x is this marked element. And we basically want to determine the marked element. Okay, so we want to see which of these 2 to the n possible f's is actually our input. That's what our algorithm wants to determine. And again, we're going to work in the query setting. So, we're given an oracle access to one of these f's. And since x kind of determines the f, the marked element determines the f, I'm just going to denote the oracle by ox. Okay? So ox, is the oracle for the function f such that x is the unique element with f of x equals 1. And I'm going to work in the phase version of the oracle, okay? And I'm also going to drop the control register, okay? So I'm just going to say that we have an oracle ox, which on a basis vector y, it multiplies the phase by -1 if y is equal to x, and otherwise it does nothing. Okay, so that's the oracle that we're going to be working with in this lecture. So again, what's the setup? We can use this oracle ox, and we want to determine what x is. So that's our goal is. So we want to determine x. And we want to do that with as few applications of ox as possible, and hopefully also by means of a small circuit that uses these ox operations. Okay, so let's see how we can do this. Okay, so it's going to be helpful to think about this oracle in a more geometric way. Okay, so you can see that you can write ox just as the identity -2 ket x bra x. Okay, so this is actually just a reflection about the plane orthogonal to x. Okay, so again, we're just multiplying the component of the state parallel to x by -1. Okay, so x, of course, is one very important state for our algorithm, and the other important state for our algorithm is the uniform superposition. Okay, so just as with every algorithm we've seen, we're going to start off by first creating the uniform superposition. Okay, so actually the whole algorithm is going to take place just in this two-dimensional plane spanned by the uniform superposition and x. Okay, so the picture is kind of going to be the following. So here we have the state x, and here we have the uniform superposition. Okay, so note that the uniform superposition is not orthogonal to x. Okay, so it would be somewhere over here. Okay, so we start out in the uniform superposition, and we want to apply our algorithm so that at the end of the day we get a state which is very close to x. Okay, because if our state is has a very large overlap with x, then with good probability when we measure, then we're going to see x. Okay, and then we'll have the right answer. Okay, so that's the basic idea. We're going to start out in this uniform superposition, we want to get to a state closer to x. And the state of our algorithm is always going to be in this two-dimensional plane. Okay, so we're actually just going to do a sequence of rotations that is going to move this vector, the uniform superposition. We start out there and then do a sequence of rotations to get closer and closer and closer to x. And then once we get close enough, we want to stop the algorithm and measure. So that's kind of a very high level intuitive picture of what's going to happen. As I mentioned, we're going to start off in the uniform superposition, and then we're just going to do a rotation in this two-dimensional plane, which is going to get us closer to x. And more precisely, the rotation that we're going to do is defined by this. Okay, so it's a product of two reflections. This is just our oracle, and this one is a reflection about the uniform superposition. Okay, so the product of these is going to be a rotation. We call that the Grover iterate G. Okay, and our algorithm is just going to be to create the uniform superposition. So this creates the uniform superposition, and then apply this Grover iterate k many times for an appropriately chosen k. Okay, and that's going to be the whole algorithm. And it turns out that this Grover iterate can also be implemented efficiently, with the Oracle access. So this part of the Grover iterate is just an Oracle query, okay? And then this reflection about the uniform superposition, you can actually implement by a circuit with just a linear order n many gates, okay? So that part I'll actually leave as an exercise for you. So let's look a bit deeper into this two-dimensional plane in which the algorithm is going to take place. Okay, so as I mentioned before, the two-dimensional plane is spanned by the state x and by the uniform superposition u, okay? But it's going to be convenient, working in this two-dimensional plane to also know what this vector is. Okay, so this state in this two-dimensional plane and orthogonal to x. Okay, so that vector is just going to be what we call u prime here. Okay, so that's going to be a superposition, uniform superposition over all basis states, not including x. Okay, so clearly that state is orthogonal to x, and it also lies in this two-dimensional plane. I mean, you can write this state as a linear combination of x and the uniform state. Okay, so that is our other axis here, is u prime. Okay, and we can also see how to write u, the uniform superposition, as a linear combination of u prime and x. And how do we do that? Well, I just multiply u prime by square root of n minus 1, so that kills this normalization term here. Okay, and then I just add x back in, right? So this state is just sum over all y in 0, 1 to the n, ket y, including x, and then I renormalize it. So then I divide by 1 over square root of n. Okay, so that's how we can write the uniform superposition in terms of our unit vectors labeling our axes here. Okay, so here we have our picture again. So we have x, labeling this axis, u prime labeling this axis. We've expressed the uniform superposition as a linear combination of u prime and x. And now the question that we want to ask is, what is the angle here? What angle does u, the uniform superposition, make with u prime? And we can see that just by looking at the inner product of u and u prime. Okay, so you can see that that is just square root of n minus 1 divided by square root of n, or in other words, square root of 1 minus 1 over n. And this inner product is just the cosine of the angle between them. Okay, so so that means that the sine of this angle is going to be equal to the square root of 1 divided by n. And so the angle is the arc sine of square root of 1 divided by n. And since sine of theta, for small theta, sine of theta is roughly theta, right? That's the first term of the Taylor approximation. So we can, roughly, for our intuitive picture, we can kind of think about this as square root of 1 over n. Now let's look at the action of the Grover iterate. And we're going to start out by seeing what the Grover iterate does to the uniform superposition. Okay, so let's say we start out in this vector here, the uniform superposition, and now we apply the oracle. Okay, so that's just a reflection in the plane orthogonal to x. Okay, so since we start out making an angle theta with the state orthogonal to x, then this is just going to flip us down to this state here. Okay, so now we're in this state psi here, and now we make an angle of 2 theta with the uniform superposition. So next we're going to apply this reflection about the uniform superposition. Okay, so that is going to flip us up to this state here, psi prime. Okay, so now we're going to make an angle of 2 theta with the uniform superposition on this side, right? So now we've actually gotten 2 theta closer to where we want to be, right? The state x. Okay, so the net effect of the Grover iterate when we started in the uniform superposition was to rotate us by an angle of 2 theta closer to x. So again, summarizing, when we applied the Grover iterate to the state u, we ended up in this state here, psi prime, which was a rotation by an angle 2 theta counterclockwise. So we actually got 2 theta radians closer to the state x. And this is actually what the Grover iterate is going to do to a general state, not just u. Okay, so the Grover iterate actually defines a rotation counterclockwise by an angle of 2 theta. So let's see why that's the case. So again, a really nice thing about analyzing Grover's algorithm is that we can just think about everything in this 2-dimensional plane. Okay, so I can actually, represent the action of G in this 2-dimensional plane, as just a 2 by 2 matrix. Okay, so again, my basis vectors in this 2-dimensional plane are u prime and x. Okay, so what does this operation do, right? Identity minus 2 ket x bra x. Well, that just multiplies the component, the x component of a vector by -1. Okay, so in this basis, u prime and x, the matrix representing this action just looks like this. Okay, the component here, which is the reflection about the uniform superposition, so this is slightly more complicated, but we can understand this as follows. Okay, so how do we reflect about the uniform superposition here? Well, I can think about that by first rotating the uniform superposition down to the x-axis. Okay, so that is just a rotation by theta in the clockwise direction. Okay, so first I rotate by theta in the clockwise direction, and now I just do a reflection about the horizontal axis. Okay, so we already know how to do that. That's exactly the same as this action of the oracle. Okay, and then finally I rotate the state back by an angle theta. So by an angle theta counterclockwise. Okay, so so this is how I can write the reflection about U, as a composition of these three actions. Okay, and now we can simply, multiply these together and multiply that by the action of the oracle here. And if you do that and then simplify with some trig identities, you actually get the following matrix, which is exactly a rotation counterclockwise by an angle of 2 theta. Okay, so that tells us that the general action of the Grover iterate is to rotate a state counterclockwise by the angle of 2 theta. Okay, so now we can start to analyze the success probability of Grover's algorithm. Okay, so recall that the state U is just the state cosine theta U prime plus sine theta of x, okay? And now G has the action of rotating the state by an angle 2 theta counterclockwise. Okay, so after applying G k many times, we are just in this state here. Okay, cosine 2k plus 1 times theta is the amplitude on the U prime state, and sine 2k plus 1 quantity theta is our amplitude on x. Okay, so after we do this and we measure, the probability that we're going to see x is the sine squared of quantity 2k plus 1 times theta. Okay, so you want to choose k to make this as close to 1 as possible. Okay, uh, so this would be 1 when the argument here is pi over 2, right? So we basically want to choose k for this to be as close to pi over 2 as possible. So the choice that makes this pi over 2, the choice of k is pi over 4 theta minus a half. Okay, but kind of the rub is that this may not always be an integer, right? Whereas of course we need to apply g in an integral number of times. Okay, so what we're actually going to do is to apply the Grover iterate m times, where m is just the floor of pi over 4 theta. Okay, so with this choice, then the distance between m and the optimal choice is always at most a half. Okay, so the distance between m and m bar is always at most a half. Okay, so basically what this means in terms of our picture is we would like our final state to be x, of course, okay? But when we apply the Grover iterate m many times, what we can actually guarantee is that our state will be in some small region here. So we can guarantee that we'll be in this region here, and because the distance between m and m bar is at most a half, then basically we're going to deviate from pi over 2 by at most an angle of theta on either side. Okay, so this angle here is going to be at most theta. Okay, so that tells us that when we actually apply the Grover iterate n many times, we can lower bound the value of the overlap with x, right? The overlap with x is sine of 2n plus 1 quantity times theta. So that overlap is going to be at least sine of pi over 2 minus theta, okay? And that's just because, the sine function is symmetric about pi over 2 here, and it's increasing on this interval from pi over 2 minus theta to pi over 2. Okay, so basically our success probability is the worst if we are, one of these vectors defining this region here. Um, so as far away from ket x as possible within this region. Okay, so our overlap with x is going to be at least this, sine pi over 2 minus theta. But this is just equal to cosine theta, and we know exactly what cosine theta is. That's just square root of 1 minus 1 over n. Okay? So that tells us that our success probability, the chance that we see x and measuring at the end of the algorithm, that was at least that was exactly sine of 2m plus 1 times theta squared. So that's going to be at least 1 minus 1 over n. Okay, so that's pretty good. Okay, so let's summarize what we have here. So we're going to apply the Grover iterate for the floor of pi over 4 theta many times. And we just saw that that's going to get us success probability at least 1 minus 1 divided by n. Okay, and how can we bound this number m? Okay, so we know that the sine of theta is equal to 1 divided by square root of n, right? That just comes from the definition of theta. And we also know that the sine of theta is less than equal to theta, right? The Taylor series goes like sine of theta is approximately theta minus theta cubed over 3 factorial. So sine of theta is going to be less than theta. So that means that pi divided by 4 theta, that's actually going to be less than pi over 4 times square root of n. Okay, so we can upper bound the number of iterations of the Grover iterate we're going to do by pi over 4 times square root of n. Right, because the theta here in the denominator is actually bigger than 1 over root n. Okay, good. So each application of Grover iterate, so this part here is just a query. This part here is just a query. And then this part, I've left to you as an exercise to see that this can be implemented by a circuit with just order of n many gates. So to summarize, we can achieve success probability 1 minus 1 divided by n after order square root of n many queries and a quantum circuit of size order square root of n times log n. Okay, so again, because little n here is log of capital N. Okay, so just a couple of notes about Grover's algorithm. So, here we considered the case where the input was a function f from 0, 1 to the n to 0, 1. Okay, and we wanted to find the x such that f of x was equal to 1, promised that there is exactly one x for which this is the case. So in applications of Grover's algorithm, you usually think of it a bit differently. Okay, so usually we think of the input to Grover's algorithm is just a Boolean string z. So it's just a capital N bit string. Okay, and what the oracle does is you can query a number I. Okay, so I is just a number between 1 and n. So you query I, and it tells you the ith bit of this string z. Okay, so this is typically the scenario in which we apply Grover's algorithm. So again, in this case, you would have the promise that there's exactly one bit of the string that's 1. okay? And then you'd want to find that I such that zi is 1. Okay, so you see that in this case, capital N is not necessarily going to be a power of 2, okay? But that's not a big problem. When capital N is not a power of 2, we can still use, say, an approximate Fourier transform to create the uniform superposition for the start of the algorithm. Okay, and then everything else goes through as before. Okay, so in the future, when we look at applications of Grover's algorithm, I'm usually going to apply it in this way.